introduce Erez, who has been instrumental in getting this whole IAP session going. And he was really the seed of the idea, so we all have him to thank. Erez has spent his career helping companies solve problems using applied math, computing, and data science. He's led data science for Amgen's medical device division. He's worked in management and business development roles at Wolfram Research. He's done a bit of everything. And he's currently an MS MBA candidate and a researcher at MIT, where his work is on application of machine intelligence to large enterprises. And I think he's going to tell you a bit about a new startup that he's involved with. So go ahead, Erez.
Thank you, Craig, so much for a kind introduction. And thank you, everybody, for kind of lasting through all the sessions and being here with me and for your time. So what I'm going to talk about today is something I guess, spent the last maybe 5 or 6 years of my life doing, which is, you could call it computational thinking in startups, or how to kind of structure things into products. I would say this is almost computational thinking and solving enterprise level problems, or the business of AI. I was lucky enough to work at Wolfram Research kind of early on in my career and be involved in a lot of different solutions work, kind of large scale development, and see what people are really trying to do with AI in a company that has been doing this for a long, long time. And I say AI in a very broad sense of maybe the use of computers to replace kind of manual labor, replace thinking processes, or maybe inspire thinking. And then I later transitioned to do the similar work internally at a company called Amgen. And what I'm going to present here today is kind of the methodology I've learned at places like Wolfram and kind of brought with me and grown over time, and what I do every day when I'm trying to solve problems for internal customers, external customers, or right now when I'm trying to develop my own business to solve these type of things. And right now I'm a part of the Leaders for Global Operation program here at MIT, where I'm doing an MS MBA program with my MS in the Computer Science and Electrical Engineering department. So I'll just start, and I'll start with actually taking one step back and talking about computational thinking, because when we started designing this course, I started thinking about computational thinking, and I said I'm originally from Israel, so I speak Hebrew, and I translated into Hebrew, and in Hebrew it's called chashiva chishuvit. So chashiva is to think, and chishuvit is to compute, or it's computational thinking in female pronoun. And that sounds kind of weird. Like if you just look at this for a second, you notice that both thinking and computing in Hebrew, which is a kind of an old language comparably, they both have a lot of similar letters. And that's because both of these words come from the same root. And in Hebrew, computational thinking, computing, thinking can mean a lot of different things. So it can mean, to think, it can mean to be a bookkeeper or an accountant, someone who is doing that thing. And it could also mean to calculate or compute, which I thought was kind of weird. So the computational explorer that I am, I kind of wanted to get to the root of this issue and understand really why that is sounding so weird. And I found out that chashav, which is the root of chashiva, which is thinking, or chishuv, which is computing or calculating, comes from a very old language from Phoenician, which is the first language that had an alphabet. And in Phoenician, there's a lot of words that are kind of the form of, instead of past, present tense, they have also a command form, the same in Hebrew, which is go do something. And it was the command form for thinking. It was like, you tell someone to go think, which sounded kind of weird to me. Like, where did this come from? How is it all, obviously these words started in the same way. We had a very long history, diverged across, kind of English, apparently, to two very, very different sounding words, computing and thinking. But now we're kind of coming back to it, right? They're linking back up again. And I found that word chashav comes from the word associated with the word of using an abacus. So it's like telling someone, go use an abacus to calculate the stock on my ship. Phoenicians were seafarer people that did a lot of trading. So they had a lot of use for people with abacuses at ports and telling them to go do this. And it kind of made me think, that makes a little bit sense, that instead of this philosophical sense of thinking that we think about, early languages were very practical, and they had a very practical term, which meant go use an abacus and solve this issue for me. And through time, this kind of word in Phoenician that's still, it's amazing that modern Hebrew, which is not the form of biblical Hebrew exactly, kept a lot of similar shapes still to the Phoenician word. This is the original spelling. But it also transitioned through Egyptian, through hieroglyphs, where there it became from go thinking, it became a title for the person who is doing the thinking with the abacus, which is the bookkeeper or the accountant. And I thought that was kind of a fun story to talk about how an idea that started in the same place and diverged in the last 3,000 years into two different disciplines of thinking and computing. We're now kind of in the first years of the 21st century, or the second decade of the 21st century, thing that these things are coming back together, representing the same thing. But that's a little bit of a sidetrack that I just wanted to share. I know there's some Hebrew speaking folks in the crowd that might enjoy that, and others. And I'll just go right into it. So this is the table of contents of what we're going to talk about. I'll give you a second to review it. We're going to go from kind of some definitional stuff into some more business organizational stuff, into actually the core of the talk, which is about solving problems, doing a little bit of Mathematica, and showing some ideas and examples. So like Etienne talked about, there's kind of two different things that people tend to connect together. There's this idea of artificial general intelligence, which is some AI that can really mimic the human intelligence, whatever that might mean. And then there's kind of the more modern real world applications, which people start to call narrow AI. And I'd like to bucket all that in kind of this narrow computing workflow, which is task specific forms of computing and problem solving that are trying to do a particular thing, not a broad set of things. And usually when you think about these things, like actually Etienne kind of said, there's some objectives, right, that are that we think about, like I would like to someone to answer my phone calls and schedule an appointment, and that turns into a task because I want to visit a doctor. Maybe that's a better objective. And then there is a task of I would like to. It's a way to perform this objective. And then there is an agent that performs that task, and that agent's success is measured against that objective to some fidelity, right? Usually you need to generate some way to measure the success of that objective. And objectives, it's important to understand, are innately human, right? Humans are the people who create objectives to solve, and I and many other people don't think that in any time soon a computer will be able to generate true objectives. So I would say that people have objectives which they achieve with tasks, which are done by an agent, which is measured against those objectives. And the objective generation has into it a lot of biological data, sociological data, psychological data, all our experiences basically living on this planet, which we want to generate an objective. For example, I want to measure the price of a stock at some future date. I want to predict that. That's an objective. And now I'm finding a way to perform that as a task. Or maybe my objective is to create wealth if we go one step further. And this is just a task, a way to create that. And then I have an agent to do that. And agents don't have to be computational, right? An agent, we know from management studies, kind of the agent principle problem, for example. So for many years, agents have always been people. And now we're able to transition some narrow tasks into computers. And the main point I want to deliver through this task through this lecture is because AI is so narrow today, it's actually a much better fit for kind of created tasks that exist commonly across enterprises instead of consumer-facing tasks, right? Like it is what I want from a computer in my personal life or from any kind of agent to perform something is much broader in some sense than what an enterprise might want, right? Because enterprises are trained to have different agents fulfill a task. So tasks tend to be more quantifiable. And through this talk, I hope to show you that, we're just going to see more and more of those things happening in the enterprise space instead of in the consumer space. And that's just going to continue to develop. And how does this connect to kind of the lean startup methodology? There's a great book about how to start companies, how to kind of think and iterate really, really fast. I think it's mainly was designed originally for websites and kind of .com type startups, but now we're in a different stage where we have a lot of other types of startups that can be very computationally sophisticated. And we're very, very lucky. Even when I started programming pretty seriously, I was working at the time as a theoretical physicist, every job had to be run, and this is not that long ago, every job had to be run on a server. You had to wait for the server. You had to first work in a lab that owns a big enough server. There was kind of always a queue to run the jobs. Jobs could take, days to months to run in a very, very large simulation. And all that isn't really true today, right? Computing is actually super, super cheap, and it will continue to get cheap. It's very easy to spin out um, very big sessions on, some cloud provider's infrastructure and start doing stuff. The other thing that's very critical is that if you look, back at '90s at neural networks from the '90s, you had to kind of construct it by yourself, and there weren't really big libraries. If you wanted to do it, as many hedge funds already did, they had to build it internally for themselves. And because of these building blocks, the TensorFlow, the Wolfram language, the PyTorch, the Hugging Face, or whatever not you want, iteration becomes very, very quick. So it's very easy to iterate very, very quickly with a small group of people and produce results that are pretty interesting. So it's quicker to validate than it used to be. And that all starts with a customer. So like in every business, you should be very, very, very focused on a customer. It's not a research project necessarily, right? There's like the research things that are kind of at the forefront of what can be done. Then there's the wave behind that, those academic institutes, which is kind of the new emerging technology, whether an internal team or an external team like a startup developing them, but they have to focus on what customers actually want and not just what they want to build. Because customers have the data and customers have the objective, and customers give you the data to fulfill that objective and use that data to model something about the data. And then those models that you use to model the data, and it could be many different ones together, can be composed or interwoven together, what we're going to talk about, to create an agent. And that agent can perform some tasks on that data and can be measured against the data to fulfill the request of the customer. Another kind of interesting feature in 2021 for this entire space is the fact that you don't need that big of teams to do this work. You actually only need 3 true departments, which some people miss and think it's kind of a mishmash of things, but I hope that I can clarify a little bit about what these 3 departments is. And I'd say the first department is the data engineering, right? So there's a curation process there, which is just kind of giving proper ontology to different data points and different ideas and connecting them and curating them, putting them aside, like Wolfram Alpha has done very, very well. And I think for many, many years, if not still to the day, it was one of the largest, if not the largest, curated data set in the world, with about 10 trillion entities. Then you have a team, right, a kind of a different team than the curators, because the curators are usually subject matter experts to an extent, that builds the pipelines, right? There's the software developers that create the way of you to take large volumes of information into your model, into your agent, and produce something with it. And then finally, you kind of have the DevOps, IT that are more classic from other software companies. After that, you kind of have a modeling group, right? This is where the data scientists and machine learning engineers sit. I call them algorithm developers. And you have also kind of the support team that helps them wrangle data sets, structure them a little bit more after curation, kind of serve them so they don't need to do exactly everything, right? Some people have studied to perform these very specific algorithm tasks. They are used to working with more structured data sets, and in an enterprise business environment, it's better to provide them with that support because they're able kind of quickly to leave companies and transition between industries if they want. So there's a big tendency in large companies when they're starting up these organizations to think all of this is actually this one person. He does or she does everything, which is, causes a lot of dissatisfaction across. And finally, there's product, which, in business speak, we'd actually call the sales and marketing. In startup world, it's product, because product is over everything. But it starts with, having sales women, marketing women to help sell and market and design the kind of front-facing, customer-facing interaction. There's product development teams which help understand the client needs and help assure that the algorithm, the data pipelines, and all that work and roadmaps are properly structured for the specific need we're trying to solve. And then there's a lot of designers. And the reason I bucket these in 3 different groups is because I think there's 3 different profiles of people. These are obviously more commercially inclined folks that want to do more client-facing interaction. This group tends to be people who have usually kind of advanced degrees, sometimes not, because they have a big portfolio and they've worked a lot. Sometimes they are with advanced degrees in these specific spaces. And then I'd say the data engineering, and I think this is kind of, again, uh, a big chunk of a lot of different departments, is more software development, curation support, which is a very, very important function. And at Wolfram, like Kelvin Masco said last week, there's big departments doing that to perform what we want. Another very interesting aspect of this is that you can outsource actually a lot of the data engineering and modeling work. There's a lot of great shops that help you do that to some level of fidelity, but many times people need to understand what they can and cannot outsource. To algorithm developer, it might be harder to outsource if you have a very difficult problem, for example, some problem in processing, biopharmaceutical processing, which requires a combination of kind of data science, physics knowledge, chemical knowledge, biology knowledge. You know, there's not that many people who serve that particular market. So you'd probably need to develop it internally. If, on the other hand, you're trying to create some image processing classifier, you can probably find some algorithm developers, algorithm shops, whether the US or offshore, to support that kind of work. And by the way, if anyone has any questions, feel free to ask it as the talk goes on. And then I want to talk a little bit about what is computing as I see it, as a process where there exists data, right? A customer has, but whether internal or external customer has. That data, we need to perform some feature extraction on that data in order to turn it from, for example, numerical data or textual data into more computerly adjusted form. You know, if you have an image, you can't really do anything directly on the pixel space. You first want to take it into some numerical space, turn it into a vector. Then you have an agent that you construct to perform the task, right? The objectives. And then you need to deploy that agent and perform quality assurance on it to continually assure its fidelity, because these agents, unlike almost classic software packages, are a little more complex in the sense that maybe there's a new data point that the agent interacted with that is not well represented in the historical data set, and the agent is not ready or not trained to provide a solution to that. That's why you have a lot of quality assurance on it. But at the end of the day, there's a customer, and that's the human that has the objectives, who provides you with the data, whether you're an internal or external company, and is consuming the deployment and is requiring you to assure some quality assurance of what you're doing. So that kind of process is how I look at it. I usually go to who has the data. When I was working internally at a company, I would try and understand what kind of feature extractor needs to be built in order to turn their data into something computable. And then I would rapidly construct several different agents to try and show them what can be done with this data and interact with them continuously, and then obviously deploy them and have them assure the quality that it's on the level that they would like. And because I use the word agent in a very, very, very general sense, I find the Mathematica is a great way to do that, also because I know Mathematica very, very well, but I think it has some inherent features that make it kind of a great place to do this. And this is just a kind of an example of the top level documentation of Mathematica that we'll touch in a little bit about. And it just, to me, it breaks up really, really well all the different disciplines of computing and things you would like to do with a computer to achieve some particular task or goal. And when you build agents, right, people talk a lot about AI and these neural networks and other Markov chains and other statistical models, but there's actually a host of different things you can do to build a good agent. One would be correctly using a statistical model, right? Like some model that learns some data distribution and produces some inference on new incoming data that's out of sample. There's deterministic models that whether they perform specific tasks or that are predefined, or they just kind of calculate different things like partial differential equation solvers that need to be used in a lot of different things. You know, your ABS in your car uses some kind of deterministic model to explain how it needs to brake properly. And that has existed for a long, long time. Then there are expert systems, which used to be all the rage in the 80s and 90s in AI, but people have slowly kind of forgotten about them. But they are really a core of any well-functioning agent, I believe, because expert systems are rule-based systems that combine data and ontology of those rules to produce some result. For example, Wolfram Alpha, I think, is one of the largest expert systems ever built, and it can solve everything from integrals to asking it the size of insulin or the size of ibuprofen, or calculating the weight of ibuprofen over the weight of insulin, and kind of a broad set of questions like that. And really, expert systems are what had a big push in the AI space in the 80s and 90s, like I said. And they create a few different kind of rules. They all started really in the 60s. There was a first system that did a lot of integrals. They had like 30 integration rules, and it was a big thing. And then they had some systems for healthcare that were forecasted to replace doctors one day, because they have all this kind of ontological data and all this classification data about diseases. And then someone comes to this robot or this expert system and says, I have these 3 symptoms, and it gives probabilities of what type of diseases you might have. Obviously, that did not end up replacing doctors, and the jury's still out when that'll happen and how that would look. I don't think we're not going to go to human doctors at any point soon. And the last thing that I think is very important to think about is constraints. So you can build all these models with statistical models, with deterministic models, with expert systems, but you have to build constraints on them because they limit their behavior. And like I'm going to show in an example about image processing in a little bit, the combination of statistical models, deterministic models, and constraints is very, very powerful, and allows you to do a lot of things that people would like to see, like almost one-shot learning, or two-shot learning from 2 images, and kind of using a lot less data to provide a result, while also limiting the types of behavior your agent has, because you also don't want these agents to misbehave. This is a chart I want to stay around for a little bit on and hear maybe what people think. And it is a chart about how when I worked both internally at Amgen or externally with customers at Wolfram, and now when I'm kind of trying to build a startup exactly on this idea, is how I think of things. The first thing you need to do is to find customers. Or if you're a more technical person, you prefer just program, you find someone who will find customers and talk to these customers. Then you need to talk to the customers and understand their systematic tasks. What are the things they do routinely that are also true not just for that company, but for many other companies in their space, in their industry, or for all companies, for example. All companies need to do billing in some way, shape, or form. All companies need to pay payroll, right? These are very systematic tasks that people are, a variety of less happy and more happy with. Then you need to create agents that execute those tasks, right? So someone tells you, I need you to do X, then you need to rapidly create something that does X and show it to them, right? And the faster you can do that and usually that's tied to the type of high-level language you're able to use, the better you're off. Because eventually the customer will say, no, you kind of missed that. I don't need this type of segmentation. I need this type of prediction. I need more clusters, I need less clusters, I need it to find automatically the clusters. So then you iterate, right? So you go from finding the customers, understanding their tasks, creating agents that solve those tasks, you show those agents, and then you start to iterate with the customer, kind of creating new agents, modifying them, slowly fixing them until, the customers, or kind of the probabilistic view of enough customers, is that you solve the problem. And then you need to productize that across many companies or many departments, or if you're internal, you just need to build a robust enough solution that is actually kind of, let's call it, battle hardened and is ready to actually do stuff. This is sometimes very, very catchy. And most companies today, still in the AI market or the computational market, tend to try and solve cross industry problems. Like we, for example, create business intelligence dashboards, and you can think of a few companies that do this for everybody. We create a system or a platform to build models that anyone can use. The issue is the more unspecific your product is, the harder it is to recruit people to use it and produce actually real agents with it. And I think that over the next 10 years, we're going to see a lot of companies, and you're already starting to see it, companies focusing on logistics, companies focusing on healthcare, companies focusing on manufacturing, solving very, very, very specific and narrow problems. Like we said, narrow AI solves narrow problems. And then productizing them instead of cross industries in one industry, or not one particular flavor of an industry. and they're just able to do more. One example I always think about is that people talk constantly about finding clusters and calculating clusters. But at the end of the day, you know, in logistics and supply chain, people tend to call the clustering of products ABC analysis, and they'll never understand what clusters are. But most people in supply chain roles understand what ABC analysis is and are able to do that. So why do I use Mathematica for this? And I'll do a little bit of a short demo after I explain this. First and foremost, because I can prototype very, very fast in Mathematica, and I think most people who use it long enough can do that as well. Very, very fast. You know, the amount of code you write has been shown in studies to be about 90% of Python code across many, many different tasks. You know, just the amount of kind of strings or tokens you need to use to actively write the code. The second thing that I really love, especially when you're doing early stage rapid prototyping in front of customers or with customers, is the API compatibility, which in some ways allows Wolfram Alpha to exist, which is, you know, the APIs, the functions are very well structured and are very similar to each other, both in name and actually the way they ingest parameters and map across different things. And that allows you to transition between one discipline to another and just rapidly kind of just say, you know, let's map some abstract function on this data, and then I could just change the function later, maybe even in front of the customer, very, very fast. And so the next power is kind of that it's cross-disciplinary, right? I studied physics and math as an undergrad. I'm a computer scientist, but I a lot of times want to do stuff with natural language processing. I want to do stuff with biological data, and Mathematica kind of allows you to abstract all the details of that and think in the terms you prefer thinking. The fourth thing is there's structured external databases. So you can connect to external databases and retrieve information from them, compare them to your existing information and see what's better or produce kind of interesting results. There's a lot of great documentation, which we'll go through. I think this is kind of a point some people miss about. The documentation is really well structured. It's the same across any discipline, any function, and it provides a lot of interesting things like suggestions of other functions to use that I've found very, very, very useful. And again, finally, prototyping speed. You can prototype fast, you can show stuff to customers fast, you can move fast. So I'll kind of take us through an example workflow that I just thought about producing. Let me just, wrong. Here we go. So, you know, Mathematica notebook, you know, we all saw kind of Calvin, what Calvin does and kind of the basic structure. I'd like to start with using kind of the Wolfram Alpha database to get some stock information about a particular stock, let's say Amgen stock price last 5 years. And it's kind of easy to get that data and structure it and just plot it immediately, right? It's some kind of time series object. Let's call it TS. And that time series, we could just plot it quite quickly. Plot it quite quickly and just see how it looks. And then we can also do other stuff to it, like, you know, let's see a 30-day moving average of that. Just to see what the real kind of underlying structure is a little bit and get rid of all this noise to just smooth it out. So pretty easy to do that, right? And plot and perform some analytics. But let's take that entity again, this financial entity that is Amgen, and see what kind of other properties it might have. So it has a very, very big, long list of properties, a bunch of different things. You know, one interesting thing again might be the website for it, right? What's the website for Amgen? It's probably amgen.com, right? You can look at that, and then I actually want to do something with that website, like I want to scrape it in some way. So I want to take the full form of that. I can grab this kind of web page, and then I want to import it and look at a bunch of different elements it has. And this just lists out kind of the different things I'm able to import from that. So example images, right? I just want to import the images from that, the first page here that I'm logging into. It's going to take a second. And then the next thing I want to do is think of something to do with those images. So what can I do with images? Nice drop-down menu here. Image contents is a function I like, because it just kind of tells me the different contents in an image. So let's take that, let's run it across, map that function across all the different images we just got. This kind of / and is just the function mapping across some other expression, and this percentage sign is just the last output I got. So I run it across it, and it's going to retrieve different contents in that image. And then you could start specifying things, you know, only pull some specific content that I'm interested in. For example, only pull, you know, images that have someone with a necktie or something like that. And again, this is kind of an example I thought about earlier on, you know, different people. Bob Bradway, you see, he's wearing a necktie, so it finds that out. And that kind of made me think, how do I do to finish this demo kind of neat, or what other things I can do? So I went to image contents. Where do I go from here? And the question mark kind of gives me some information about this function. Then I can click here and open the documentation of this particular function, right? The documentation is the same for all functions, and most image content functions. Sorry, this is actually, I wanted to go to image contents. Image contents. I just get an image and it produces a data set, explains everything, it explains me all the options, it gives me, you know, examples of what to do with this. And one of the things I love the most is that at the bottom, it suggests other things you could do that are similar to the task you're trying to do right now. I particularly want to see image contains Q. Q is always kind of a true false primitive in the Wolfram language. So this is a question, it pulls some neural network, identifies different things in the image, partitions them, and then you can ask it a question about them. Does that image contain this particular category? So let's just go to this image contents queue. I want to check who, and this is output. Output 8. Where's the necktie? So let's just, this sets up a pure function, necktie. Now I'm pulling an entity called necktie, and I want to map this function across everything from input 8, from output 8. So now it's going to go and give me true false if that image contains a particular object like a necktie. Now, as it runs, I kind of thought, this is interesting. It's a little bit of a toy example. What can I do here that's actually interesting to see? You know, there's some images, true. So I thought about what Kelvin mentioned last week about how to use this for kind of managerial accounting to assess and perform due diligence on some companies. So I thought maybe there's two different companies that I can tell something about based on how many people in their about page or their leadership page wear a necktie. So I kind of took two very different financial firms. One is Apollo Asset Management, which is a global private equity firm. The other is Bessemer Venture Capital, which is a global venture capital firm, right? They invest in very, very different companies. They try to present a very different public face to different people. So let's just look how this looks if I kind of calculate it for those two different groups. So let's just, same workflow we did earlier, right? Let's import some images. And it'll give me true, false about this. And then let's just count how many trues and false. And again, everything is kind of very similar, right? It's pretty easy to prototype quite fast here. And now let's just take the Apollo and take the same thing, put it here and just replace this with the Apollo website. And we'll let both of them run for a second. And what we're going to see is that, you know, private equity websites, although this is a very small example, but I think it probably is pretty true overall. Private equity firms will have more people that are dressed more formally, more Wall Street, more with a necktie, presenting a more serious business a look. And this takes it a moment to run because I'm asking it to do a lot, right? I'm asking it to import an image, a series of images, and then calculate, you know, apply a neural network on each of these images and then count them. Counting is actually quite fast. Importing the images, scraping the web, and then doing this takes a little bit of time because it needs to load the function. Any questions while we wait on this from the crowd? Anyone? No? Perfect. So you can kind of see that there is no one in Bessemer Venture Partners wears a necktie. Well, in Apollo, it's kind of 50-50, maybe yes, maybe no. And you can imagine that you can use this again to scrape something, ask different things about images. And this is really the power of why I love to use Mathematica, is because in this kind of tiny little snippet of code, we're able to see, if this idea works, if it kind of is true on some data set, very real world and wild data set, and if it's useful. So maybe I'm trying to perform some due diligence and it can be useful. But let's close that for a second and get back to what we were talking about. So for more ideas and examples about why, what you could do in this space, because I develop a lot of Mathematica, I'm going to show stuff that I've developed in the last few years in Mathematica. I'll try to run through it and leave some time for questions. So the first thing we're going to look at is a B2C product. My father-in-law actually came to me and said, I have this idea to build something that helps assure the safety of children in pools and home pools, right? Apparently it's the leading, or one of the 3 leading causes of death of children. It's the leading cause of death of children under 4, drowning in pools. 90% of drowning happens while there is an adult supervising. There's a very narrow task we're trying to perform, right? Like understand if a child is in distressed is the final example. Is he about to drown? Maybe the first thing we want to know is if a child is over or underwater, right? Maybe I say that in my pool, people can't be underwater for more than 20 seconds or 30 seconds because I don't want people to do that. And can we build an agent that does that? And actually, this was an open question for me. Can I do it? I didn't see too many great solutions for this. So I thought maybe it'll be a little hard. So I curated data. I have a very loving wife that does these things with me. And we just went and did this together, curated a bunch of data, and I developed this as a final project for one of my classes. So let's just look at this agent architecture, for example, because it combines a lot of things we talked about. It combines an expert system, a statistical model, a deterministic model, and constraints. So first of all, there's an image, right? A client image that goes from their pool camera, this very sensitive data set, into our system. The second thing I do is I want to partition the image because I know a lot about this task. And this is another example of why it's useful to perform specific tasks. And not every system can perform really well on this, but because I know the setup, right? I know there's a pool, pools have edges, there's a limited area I'm interested in. I'm not interested in anything outside of the pool. So let's start with partitioning into subsquares and then just build a classifier using the neural net repository that Etienne showed in his classify function, actually, to find which of these squares has a pool and does not have a pool. One of the issues, the blue here, obviously, of this subimage classification is where the pool is. One of the issues you can already see is that, this little toy here or myself, it doesn't classify as a pool, and that's not great. I want the whole area. I want the entire blob. So you use like a deterministic algorithm called the convex hull blob analysis saying, I just want you to fill in everything that is a closed body, and I want to select the largest closed body. This section and thinking of doing this solved a huge issue for me because I found that doing this using a pre-trained model can go from segmenting an image out using 1 or 2 pictures of the real pool we're looking at, compared to trying to learn from many, many different images. So within 1 or 2 images of this pool with a pre-trained model and some constraints on it, and some deterministic constraints, that is, I was able to kind of already segment the pool. Next thing is I tried a bunch of different techniques to understand, segment a person out, see if he's above or below water. In this particular case, you see I am that person. This is, again, a different type of pre-trained network. And there's many other smarter ways probably to do this. This is how I did it. I'm not an expert in computer vision. So I take this person out, me, and then now I need to figure out if he's above or below water. This was a very, very difficult task. I tried to feed the convolutional network tons of images. We're going to see in the next picture. I had also a limited data set and limited resources. It didn't really work. It wasn't good enough. And I found that using a deterministic algorithm called the Gaussian filter, so basically kind of averaging with a normal distribution over each group of 2 or 3 neighboring pixels, it basically, what this does is blurs the image. And it was found that if you're outside of the water, right, and you look at your face, the Gaussian filter affects you very differently than if you're under the water. It's a lot more blurry anyways. And this ended up working surprisingly pretty well. So I used a bunch of pre-trained neural network models from the model repository. I added a few kind of classical image processing techniques to increase the fidelity on this small data set. And again, this is a very, very small data set, so it's not showing something across a lot of different things, but I think it is an interesting direction that you could see just looking at the data set of under and over water images that I kind of segmented and hand segmented at some point. You see that with no filter, there's about 60% accuracy in, did I correctly classify something as over and underwater? The moment I add the Gaussian filter, it went to 100%, which I thought was, much better than I thought, and worked pretty well. And let's maybe look at a very short video of me doing that. You don't want to see me for too long. And I took off the audio of my wife being unhappy with the fact that she needs to do this on a very hot day. So let's just see, it kind of looks frame by frame, trying to classify something. This is all done in Mathematica's kind of new video processing framework called Video Map. And, red is I'm underwater, green is above water. It doesn't always catch you, but it seems like most of the time it does, and it does so quite well. Which surprised me. And if I probably ran some averaging function over, just take the decision, the highest decision with highest rate from the last 3 or 5 frames, it probably would look a little smoother. But it's doing quite a good job. It does the task we wanted. It tells you if someone's above or below water. And this was done alone by me with the data set I self-curated. So it's kind of like shows you the power of doing something. And then I went to actually show it to some customers, which were pretty interested. I have quite a few friends who said, I have a pool. Do you have a POC I could just install in my pool? I have friends who are some tech guys who already installed cameras and have a way to stream it, so they just need a model. But I ended up deciding, I'm not a person to sell consumer products, so maybe I should go do something else like I've done previously. So let's look at like just really, really quick examples of B2B products or internal enterprise products, where I think there's even more power to these techniques. And this is going to be less AI, more computational thinking. You don't always share everything you're doing with AI.
Erez, there's a question in the chat.
Oh, yes.
Before you start.
Wow, so weird. I can't see the chat. Yes. In this particular application, would you want the customer to continue to train their copy of the cluster with image from their pool with the camera? Yes, I think one of the first things, if this, would be a product, we'd want to them to take a few images of the pool they have, so we can understand the scene that's involved there a little bit better, because there's some lighting changes, and pools sometimes can be green or blue. And then we always imagined we'd have somewhere to say, this is how, from this angle, we see the pool, and we're able to segment it. Is this actually correct? So there wouldn't be a little bit of fine tuning in each specific case, but they won't be really aware of it. And by the way, that algorithm, it works if all those are filmed from an iPhone camera, but it could work from any video stream. It's kind of agnostic to what records it or how it is recorded. Thanks, Craig. Let me know if there's any other questions. So when I go into a company, whether as an external consultant or when I was working inside a company, kind of in a service function serving, I had a function that was trying to produce results for other groups, right? They come and they say, I have this business case, can you solve it for us? I found that usually this is kind of the right avenue. It's you curate the data, you make sure that you understand its structure, and then you go discuss it with the business owner. Did I understand your data correctly? And then you model it, and there's, I'm missing a little point here of you go talk to them again. Is this the right model you want? Does this look like you want it to look? Is this producing some business role? And then you deploy that solution. So this is pretty classic, right? Data wrangling, modeling, deployment, discussion with customers. 2 different kind of projects I've done over the years. Again, this is all external stuff I've done on my own time. I can't share anything I've done for customers in the past. One is just this housing portfolio optimization for some project I was doing at MIT. Like, can you scrape some database of housing prices and structures and create the best possible house portfolio with respect to how well, for example, that neighborhood is doing, right? So you have a limited budget. It's a kind of modern portfolio theory optimization, but instead of stocks, you have houses. Common task for a lot of real estate funds. The other thing that kind of was an offshoot of that, or maybe in a way actually promoted this idea, was that I saw, I think it was Christopher Wolfram, Stephen Wolfram's son, did a online session about taking this data set, which is Cambridge building permits. So in Cambridge, Massachusetts, where MIT is, apparently also the municipality is very interested in data. So they release these great data sets about residential building permits. So it's, if I want to fix something in my house, how much money am I going to invest in it? I have to give some assessment. Where am I going to do it? What's the geolocation? And so on and so forth. And I used that data set to come and pull all the different addresses from whether the address or the geolocation, I can't even remember where it started from, and then calculate year over year where all the money in the Cambridge area is going on development, with particular focus on building permits that have to do with external development. So, kind of you're thinking, wow, if there's a lot of money going here in West Cambridge, probably that the area, especially on external facing permits, that area's overall value is going to rise, right? Because people are doing that better and better. And there's ways to validate that if it's true. And this is kind of a very similar map, just one. I'm sorry, my dog here is barking. This is just hexagons, and this is more of a density plot showing that maybe if you had the money to buy in West Cambridge, that's where you should go. And it's actually surprising because it does flow over the years, and I had some nice image of that. I'm not going to get into the code too much, but so this is an example. Both of them are geographic computing with here with optimization, here with kind of a more some pooling and stuff like that of the data, which is pretty interesting. And you can imagine that applies to a lot of enterprise issues. Where are my sales going? Where should I invest soon? Where is there more budget in a particular industry that I'm interested in approaching, and so on? Or again, for a financialist to just do that. One last example I'll leave you with is an external facing product that was looking at financial complaints. I'm sorry for the image to be a little blurry. I did this a while ago. And what this does is it takes some financial complaint database that is publicly available and is given by address. And I was interested in seeing who is complaining the most to, I believe it was the SEC, but I can't be sure of that, about different financial issues with different financial products. Unsurprisingly, kind of New York, Chicago, Los Angeles are leading the charge, with Houston and Phoenix a little bit in the back, but I think New York is very clear. Well, and you can even see that a lot of the complaints are coming from the Wall Street area. So again, you can show this to someone and say, what's interesting about this? What can I find here that's important? If you're if you're working at the SEC, you probably would want to know about who's complaining more and who's complaining less, and who is underserved because maybe they're not aware of these issues, and you want to create a proper policy for that. I'll leave you with one kind of 4 final thoughts from me, one last slide, and then take any questions we have, which is what I think the future will hold. I've been doing this for a few years, both at Wolfram, Amgen, at MIT. I've been thinking a lot about this topic of where is kind of computational thinking and applications in industry going to go. So first of all, like Etienne said, I think there's going to be a lot more computing and a lot bigger models. Second, I think we're going to find that people are going to transition away from these very general, complicated AGI, artificial general intelligence applications, like autonomous driving or Turing complete personal assistant, to much more narrow applications that solve very specific businesses. And because of that, we're going to see that there's a focus on enterprise applications, because the enterprises already have processes that have SOPs, standard operating procedure. The tasks are very narrow. The objectives are logical, right? An enterprise usually has logical objectives. I want to increase revenue. I want to reduce costs. I want to do something that has some logical reasoning, not like a person who wants to do something because he's self-generating objectives all the time. And finally, what I think we're going to see really happen is that a lot of these companies that used to be cross-vertical are going to start focusing on particular verticals, whether that's just through a front end of some application or by saying, what I do is only vertical specific AI. And that's where kind of my company that's starting to be built right now is going to go. We're going to solve AI in vertical specific applications for the life science industries across pharmaceuticals, biotechnology, and medical device. Last thing to look at is this narrow AI and computing workflow again. So remember, and this is always true, there are objectives that we need to solve. This is what we're all trying to do with our life, right? We generate objectives and we're trying to solve them. this is primarily human generated. The ability to generate objectives is very, very far from a machine, for many different reasons. One of them is they just don't have that much data compared to us. Our DNA has 6.4 billion base pairs. We have 10,000 years of cultural history, maybe 100,000 years, depends who you ask. I've been living for a while, and I have all my personal psychology and sociology of my particular society that makes me think of particular things. Then there is a task someone would like to perform to achieve that objective, and there is an agent you develop to perform that task. And because of this workflow, and because of the agent today is actually very narrow, the narrow AI, the narrow computing is not a very general thing. You could imagine that this will be more and more focused on enterprise. So if you have any questions, please email me at erez@cedarlifesciences.com. We're also looking to hire a bunch of technical talent in the coming months and years. So if you're interested, please let me know. We're looking for you, technical and other. And that's it. Any questions?
We'll take questions from the audience. I have a question if nobody else does. Audience first.
I would like
Go
to
ahead.
ask a question. Hi, Erez.
Everyone, thanks for coming.
No, thank you for inviting us. It was a great talk, by the way. Thank you. What about standard tools? I mean, right now, like when you talk about tasks and agents, it seems like we have so many flavors, so many options, that it's hard to see where the future is actually heading, or the trend of like for a data scientist or an engineer working on this. What are your thoughts on that?
Yeah, I think there is, in my mind at least, what happened is there was a generation of tool building that happened. And because kind of people were possibly too scared maybe to gamble on one particular application. In the enterprise, let's talk about just enterprise, that's what I know. Let me if you don't mind, I'll put all of you here so I can see you. And then what people did is they build these platforms, right? It started with the business intelligence platforms, the Tableaus, the Sisense, the kind of Microsoft Power BI, but no one wanted to develop particular application. I think what's going to happen is that people, as time goes on, and this is my plan, is instead of developing development tools, because again, why people develop this, because they know developers, they themselves are developers, the funders are kind of in this ecosystem, so they give more money to what they think is happening. I think what's going to happen is there's going to emerge companies that develop specific application that solves very specific tasks and very specific verticals and solves them very, very, very well. Instead of saying we develop tools to solve stuff. But I think it's kind of slowly emerging. People aren't sure about the tasks. The companies aren't sure about what the tasks they want to have done. But that's my thought. I think there's more platforms than you really need almost today. And it's harder. The hardest thing is to hire data scientists. So you really, what you're trying to do is you're not trying to have a lot of data scientists. You're trying to solve particular business problems. And if you can do that without hiring too many data scientists, they're very expensive and leave and can cross industries and verticals and companies, you're better off buying, from a vendor a very task-specific application.
Makes sense. Thanks.
Yeah, you're welcome. Thank you.
Any other questions out there? Can I ask you a bit about that last point about outsourcing data curation and development work? Two questions come to mind. First, when you outsource, do you need to outsource to Wolfram language developers? And then I'll just ask the second question now. And then what do you do about development cycles and kind of institutional history, or how do you do the redevelopment of code if you outsource most of your development?
Yeah. So two-part questions are always hard to answer. So the first one was on, do you outsource to Wolfram Research, or overall, how do you outsource? And the second one is, how do you deal with kind of legacy processes and mindsets, I'd say almost. I found that I think Wolfram and my time working on Wolfram Consulting was doing an amazing job. And I would highly recommend engaging with them. And most of my professional worlds have also recommended it, just because I know they solve problems, they solve them very, very fast. They have a lot of experience doing applied mathematics, for companies kind of from the smaller scale and developing startups, basically being the entire technical part of a startup outsourced, up to solving these very, very big enterprise applications, even for companies that are very famous for being good at computing, kind of top tier technology companies. I think they're useful. I think there's other good consultants, but I've found that the companies like Wolfram, like other kind of tool providers in the applied math space who've developed consulting practices, developed it because of customer need and have real heavy insight into that. And sometimes the other groups that are jumping on this bandwagon because it's very, very big don't have the same expertise and know more about, for example, management consulting than algorithmic consulting, which is different. The second question is a hard one. And I think, I've seen it come in three flavors. One is you want to do this thing called, computing or data science and bolster your organization. You have a hard time doing that because you have a hard time hiring people. And then you don't necessarily have the type of executive management that people, that these data scientists are looking for. I've seen a lot of data scientists come to companies, friends and coworkers that will come and say, this is a great place, but I want to do algorithm development. I don't want to also like prove to you why I need to be here and convince you of these systems. I usually go to organization, and that's probably not a great thing. And I think there needs to be some re-education of helping them segment and having even inside organizations a layer of product managers that take away that concern. Like technical people are technical people for a reason, and you need to give them the right way to kind of emerge and do it. And I also think it's a new challenge where most companies, established companies, are used to, if I don't hire this person, there's 100 other applicants with similar skill set. But here, because it's so new and because there's such a high demand, it doesn't work like that anymore. Thank you. I think there's...
Thanks. Yeah. Any other questions out there?
I see there's something in the chat. Let me see. One of your examples of a B2B task was based on identifying the sources of investor complaints submitted to the SEC or another regulatory body. You indicated that your specific expertise is related to biomedical, but you do not have any insights on the development tools we might see in the legal industry in the next 10 years. Thanks. So great question by Christian Pareda, who's a lawyer, I believe, who joined us today. There's going to be a lot of stuff that replaces manual tasks, I think, in legal. Summarizing them. Obviously, no chatbot is gonna go into the courtroom and work in front of a jury in the U.S. But I think there's already a lot of tools to auto-generate documents and summarize documents. And I think that's something, again, from my experience in biomedical, I think there's going to be a lot of tools and specific applications to generate regulatory reports that are, kind of legal documents instead of writing them from scratch. I think that's going to happen pretty soon, that people are going to start saying, I don't want to write 10 pages from scratch. I want a computer to generate the 10 pages on this particular topic with my data and do it in a logical way. And I'm just going to edit that and save a lot of time. So I hope that answers that question. Anything else, folks? And also, on that legal part, I'll say that there's, computational contracts, which started with kind of financial transactions, derivative trading, right? Like call options are a financial contract, or a digital financial contract. Computational, because it can be executed according to some external data source, right? I pull the stock price and then I know the price of the option. I think that's kind of going to expand to a lot of things. There's a great blog post by Stephen Wolfram called it is about the future of AI and symbolic discourse. And it discusses how eventually these agents between enterprises that are going to control trades and stuff like that will have to work together or work against each other and have, data sorters that verify. I think the classic example is, I agree to buy from you only grade A oranges. The agent, is in charge of that interaction. The agent has some kind of image processing ability to see if they are indeed grade A oranges.